Now that we know how to solve systems using graphing, substitution, and elimination, now let's take a look at some special systems. So we'll graph these two equations. First, what we want to do is convert it to slope-intercept form. And so we have x minus 3y equals negative 9. When we want to put it in slope-intercept form, we want to isolate the y value. So let's subtract x on both sides. Negative 3y equals negative x minus 9 divided by negative 3 to every single term. So y equals 1/3 x, and negative over negative, it's a positive 3. So that is our first equation we'll graph. We start at the 3, up 3, and then our slope is either 1 over 3 or negative 1 over negative 3. So we go up 1, right 3, down 1, left 3, and then we can repeat here. And so this is our graph for that line. So let's graph the second line. So again, we want to isolate the y value. X minus y equals negative 1. Subtract x from both sides. So we get negative y equals negative x minus 1. Then we want to make the y positive, so divide by negative 1 to each and every term. That just changes the sign. So y equals x plus 1. So to graph this line, we start at the y-intercept of 1. And then we go, the slope is 1, 1. So up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. And then we see the point of intersection. Our point of intersection is here. So let's finish this line. There we go. And so the solution to our system is where the graphs intersect. And we intersect here, so we get to that by a positive 1, 2, 3 to the right, and then 1, 2, 3, 4 up. So 3, 4 is the solution of the system. So when we see one solution, that's what we've been seeing, one solution, we get an ordered pair. One solution means you get an ordered pair. The graphs intersect. We get an ordered pair, the graphs or the lines intersect. Okay, so let's take a look at if we solve a system algebraically. We want to solve using substitution or elimination. So looking at these two equations, we can't do substitution. That would be a lot of work for that. So let's go ahead and solve by elimination. So the nicest one is probably our x values, so 2 and 6, as opposed to 5 and 7. Now I say 2 and 6 because we can make 2 a 6 by multiplying by 3. Now remember, we want opposite coefficients, so we need them to look like a 6x and a negative 6x. So one way to do that, as a review, is to multiply one of the equations by something, by a constant, in order to change it. So this first equation, we want it to be a negative 6. So in order to get this first value, the x value, to be a negative 6, we need to multiply it by a negative 3. Then we distribute to every single term. Oops, keep pressing that button. Here we go. So this is negative 6x. Negative 3 times 5 is negative 15y. And then 14 times negative 3, let me do it here, 14 times 3, that is 42, negative 42. Now the second equation, we just write it as it is, 6x plus 7y equals 10. Then we add them together. So the x's cancel, which is what we wanted. When you eliminate, that cancels. And then 15 plus negative 15 plus 7 is a negative 8y. And then negative 42 plus 10 is a negative 32. Divide by negative 8. Therefore, y equals a positive 4. Now, we have to get the x value, the other variable. So in order to do that is we plug this y value into one of the systems, one of the equations. It doesn't matter which one. You could plug it into the one of the original, you could plug it into the one that you changed. But I'm going to go ahead and plug it into this one. So we have our y. So 2x plus 5 times our y value of 4. Okay, so we substitute into that equation and solve. So we get 2x plus 20 equals 14. Subtract 20 from both sides. We get 2x equals negative 6 divided by 2. So x equals negative 3. So our ordered pair, the solution to this system is negative 3, 4. So when we solve for it algebraically or mathematically, when we're trying to solve, we get an ordered pair. Okay, so the next video I will do the other two examples.